All right, in this video we're going to be talking about the VAV box family in the Mechanical Productivity Pack. This family was in part by creation by John Atkinson with the whole idea of providing information sooner to other disciplines. So doing calculations within the family, doing load calculations, sensible coil calculations, GPM calculations, and then also electrical calculations. This was actually the first family that we experimented with doing very heavy calculation-based families, and this basically started everything else that you see in the mechanical equipment configurator. So the VAV box auto size family. Let's first talk. Well, let me pull it up in the browser here. All right, so this particular family has performance in the name. Performance is something you guys are going to see more often. These essentially are very advanced families. They include CSV files as performance tables from a manufacturer. In this case, these are based upon Titus's data. And what that does is that allows you to fill in large amounts of your schedule just from the performance table. Also, having the performance table allows you to do formulas to auto size families. So there's two benefits to that. The downside is these performance-based families have very little flexibility to fit some unique condition from another manufacturer without having their performance table available. If the performance table is available, then we're good to go. All right, so the process. The first process is getting your zones done in Revit, getting the calculations done somehow, whether exporting that to a third party or to do it right within Revit, but to essentially get load data in here because this ends up driving all of the stuff downstream to what we're going to talk about. So we also have calculated airflows. So step one is getting your loads done, just like any other project. Step two is going to be getting airflow at diffusers and placing diffusers. So if we go to a ceiling plan here, as you can see, we have some linear bar grills placed. We have the actual CFM basically covering the calculated CFM. Maybe we'll increase this by 5 just so no one gets too concerned. Okay, and so step two is getting airflow to the air terminals, which we'll be showing you guys some Dynamo scripts for that process, which are going to drastically save times. But then it's getting your ductwork connected up to the VAV box. So we're going to walk through placing a heating, water, and an electric VAV box and talk about the calculations that's happening in those. So my duct is at 11 feet. So let's place some equipment. All right, so I'm going to be placing heating water VAV box, and then we'll give it an offset here of 11 feet. There we go. We can rotate this, not that way, and we can place it. All right, so right now, this VAV box, let's look at calculated airflow, which should start at 0. 0 is the default. Actually, I'm going to fix that right now. If you select a family and hit CS on it, that is now the default. Okay, so let's verify that. All right, there's our VAV box. When it's initially placed with no airflow, we have the minimum neck size. All right, so just like the diffuser families, this constraints group is the control panel for this VAV box. You have a next size and a next size input. This would be your override. So if you ever wanted to lock in a size or change an auto size value, you would enter it there. As you can see, that updated. Supply airflow input would be to, if you didn't have ductwork connected and you didn't have GRDs and you knew there was going to be so much CFM, you could enter that to begin with. You could say this box is going to have 1500 CFM, and then you can auto size the box that way. Once you do get things connected, I would encourage you to zero this back out and use your actual connected airflow so that everything stays more precise. And then we have some controls for left hand and right hand. So left hand is going to flip the box to the other side. Left hand and right hand is based upon looking into the inlet of the VAV box. So if we look into it this way, this is the left side, this is the right side. And then the coil as well, we can flip independently of that, just the same. All right, so that's some of the controls for the VAV box. Now we need to get some airflow into it, which we're going to do just by connecting ductwork. So this section of duct right now has 1565 CFM. Let's drag this in. All right, so the box has auto-sized. This is a rather odd transition, so I'm going to delete that and drag that back in. So the box is auto-sized now. We are auto-sizing based off of AHRI airflows, which is kind of a nominal range for VAV boxes. You'll notice that on heating water boxes, you have to end up upsizing more often to get your coil loads covered. For electric, though, the AHRI seems to fit in most cases. So right now we have a 12-inch neck auto-sized based on AHRI airflow. We would essentially run our loads, which we've done, and we would need to know our minimum airflow. So we can get that right from our zone checksums. So we're going to say this is 1-10. Let's move this up. Oh, I guess I've been using a space instead of a dash. All right, so this one is 1-10. Like the other families, we have a clearance volume here that can be turned on or off. So that's done in edit type. That's a visibility parameter. So right here we could turn all the clearances off. And now let's go and look at those zone checksums for 1-10. Let's open that up. All right, so I'm going to (1-10). So here's our calculated airflow that we brought into Revit. I did these load calculations in Train Trace, and my nominal vent is this. My minimum stop RH is 469. So we're going to want to enter that into the family. So one way to do that is by editing a percentage. You can say equals 479 divided by 1565. Whoops, let's try that again. Equals 100 times 479 divided by 1565. All right, so there's the exact percentage. Now we got to the 480 CFM like we need. So now we have our maximum and minimum airflows. So let's go and look at mechanical loads. So I'm going to collapse these. All right, so here's our calculated outlet duct airflow. And here is the loads. So this is the same sequence of parameters that's set up in the mechanical equipment configurator. Essentially, the capacity is that standard equation, you know, the 1.08 times CFM times delta T. The airflow is going to match. The way that we set this up is the airflow is going to match maximum design airflow if it's an exterior zone, or it's going to match minimum design airflow if it's an interior zone. So as you can see, 480 CFM was our minimum. We also have some initial design set points for leaving air temperature. This is just based upon a couple companies' standards, so you could update this 80 to be whatever you wanted for interior zone boxes. And you also see the load changed here. And not just that, but the water flow has changed as well. So this particular zone, let's take a look here. We definitely are on a perimeter zone. So I'm going to select that, and we're going to check exterior zone. Our heating coil capacity now is being calculated based upon that connected airflow and the delta T from 55 to 95. If you wanted to override the leaving air temperature, you can do that. You can use the input and you can override that to be whatever you need it to be. And then heating coil entering water temperature and leaving water temperature, these are our defaults. So you can edit these to be whatever your heating plant is. And look at, just like that, we have a calculated GPM. So I guess let's check one more thing. Okay, here's our supply air density and supply air specific heat. Okay. All right, so just like that, as soon as we connect piping to this, so I'm going to shift the piping over and we'll make those connections. Something looks a little off there. Let's take a look at this. .3/8, we have a 12-inch box. Okay, I'm gonna hold off on these connections right now for the moment. But I guess the point is that here, let's add it to the system at least. And then this one is our heating water return. So the important thing is that, let's draw this as copper, is that we have a GPM already at the pipe. As soon as you start running this out and making connections, there's a GPM to this. So under mechanical flow, so 4.8 GPM. And same with this pipe. All right, so let's connect the neck here. So be aware of that. This is it's a calculated value at the fitting, but Revit has some issues with auto-sizing some of these instance-based parameters. So I would actually start from the neck and then draw out to your duct. There you go. All right, so what do we have left to do on this? Right now, the message center is indicating that this selection is valid. However, I still will run these selections in Titus's team software so that I can get the pressure drop, so heating coil water pressure drop and the air pressure drop, so I can verify those pieces of information. So let's take a look at the design schedule now for this given family. If we go to, I actually have this placed on the riser diagrams. All right, so here is the design VAV sizing schedule. We just placed this 1-10, this 12-inch here. So you can see all the values from the properties list that we had before. So exterior zone. So one thing we haven't verified yet is the zone heat loss. So this comes from your loads, and what we need to do is we need to go to our loads. So this is 1-10, and we need to plug in the zone heat loss. So this number right here, the space peak sensible, 14,694. Okay, and so right now, this is the ventilation load. This is the energy required to raise 55-degree air up to room space temperature. And then the required capacity is the addition of both those. And then here's our capacity check against the calculated value. So in this case, we're just fine. This particular zone here, we have a situation that doesn't look accurate. In this case, this particular VAV box might need to be set to an exterior zone to raise the heating airflow to cover that. Now we're at 215%. So the blue columns are the inputs, the overrides. The green are design values. Some of these green values now we're going to get from the Titus team selection software once we're done. So let's look at that. So here's my selections in team software. What we have is NC levels. So here's 1-10. We have an airflow in MBH, a load, and essentially GPMs, and then number of rows. So in this particular VAV box, we were below thresholds for minimum airflows on a given box. So to get the coil size to work, we had to increase the size to 14-inch. So we would update that in our schedule. So we can do that right here in this schedule. We're going to apply an override. Okay, so we increase the size of the box. And now the load hasn't gone up yet. We're still at our connected airflow. And let's see. And right now we have the load covered by 184%. So at this point in time, I don't have anything else to update except for the pressure drop, the rows, and the fins per inch. So I'm going to move this over to the side here. Okay, so we're at the bottom line down there. So our air pressure drop is 0.59. Our rows is 4, and our fins per inch is 10. I'm going to change this to 4. And now team software, I have to talk to Titus about it, but there's certain conditions and they're trying to maintain turbulent flow conditions So they don't let you always get a 30-degree delta T. On any note, we're going to use the leaving water temperature here. So 116.4. And I gotta check something here. 1680. I think I have the incorrect airflow. Let's take a look. Let's go to our sealing plan. Okay, so I just flat out selected this at the wrong CFM. My mistake. And now we have a calculated flow. What's important to note is that this flow will end up matching this flow if you have the correct CFM, which I do not. So for the sake of discussion, we're going to assume that it's just fine. And now the message center is indicating selection valid. So there is a VAV box here that has a message center piece of information. Heating coil water flow is below lookup table minimum. So right now our minimum flow for these VAV boxes is 0.5. So right here. So apparently that's below. However, this is an interior zone, and I'm not too concerned about being below the minimum flow conditions, which is probably dated literature. So I'm going to leave that as it is right now. And going back to the plan, we'll close this down. So here's the family. We do have minimum flows that your company can use for coils. So there's a parameter under mechanical flow that's called minimum heating coil water flow. You could put this into whatever you want. The equations will pick that up, and this will be your minimum calculated flow. So just out of curiosity, I'm going to put this at 0.25. Actually, I'm going to put this at 0. Let's find out what that coil wanted to be. Okay, let's go back to the schedule. So that's the electric schedule. Let's go to the so that coil wanted to be 0.3 for what it's worth. All right, so that's heating water VAV boxes. The only last thing left to do is to make our connections to the given VAV box. So we can align to this, and if you hit tab, you can get to a point, and then you can align to that. There's one connection, and there's two connections. So looking back at the riser diagram down here, here was the box we just connected. So we should have, everything flowing now, and you can see 12.7. So let's place a tag on this unit. And 6.1. So it looks good. Looks good to me. All right, let's talk electric VAV reheat. Let's go up to the second floor for that. And this is the sample project. I'm going to go to an HVAC plan. Okay, so this is the box we're going to be working with right now. I'm going to delete this, and we'll just place a new box. So let's go to an electric heat 208 single phase. And let's see, so this duct is at 11 feet again. So we can put this family at 11 feet. And let's make sure we have no airflow to start. So 0. And now, so here's our starting box. So step 1 is, getting your airflow to the terminals, getting them connected, connecting the duct to the VAV box. So this duct right now has 1380 CFM. So let's connect that. So the box has auto-sized. It's chosen a 12-inch neck based upon AHRI. We have our minimum airflow that we could edit here. So let's go look at our loads real quick. This is 2-9. Okay, minimum airflow is 403. We'll call it 405. So we can say equals 405 divided by 1380. Oh, shoot, times 100. Times 405 divided by 1380. There we go. So now we got to make a connection here. This is a 12-inch duct, so I'm going to tie that in. Now we have flow downstream here. This electric box works the same way, where you can make it a left-hand or a right-hand box, whatever you want. And now let's look at the load calculations. So let's go down to, there's our calculated airflow. So here's our calcs. The capacity is this many BTU. This is going to be an electric heat type coil. And then we've got the same, default standards that we had previously. Now, this information, this heating coil capacity, is used to calculate the electrical loads. So that essentially comes up to here, and I see we have a very huge heating element power value. So we can look at the message center. Calculated kW exceeds heating element max for given voltage and phase. Select higher voltage and phase. So this type of functionality is only available because we have a performance table with these values. So let's select this box. Let's try 208 3-phase. That's not going to work. Let's go up to 480 volt 3-phase. So before even talking to the electrical engineer, this is our only option. Our only other option is to divide up this zone into 2 smaller zones. So now what we're left with is MCA is calculated, MOCP, FLA, the real power, apparent load, it's all calculated. So as soon as electrical circuits this essentially is a dynamic apparent load until they go in and override stuff, but I don't see that being very common. So they could override this, and then now the values are locked. However, this is just as the design changes, these values will update. So let's go and look at that design schedule real quick and see if there's anything else worth mentioning. So under schedules here, M_equipment or design. Here's the VAV box. So we'd want to run an actual selection of this. And I'm going to give this a number. It just so happens I've ran an actual selection. So let's take a look at that. 2-9, so we did end up with a 12-inch box. And then from team software, they're saying our MCA is 27.1 and the MOCP is 30. Let's see how that compares with our information. What was that number? 27.1 and 30. and the kW, so electric heat 18 kW. Let's see what kW we're at right now. We're at 18. That's interesting. Look at decimal places here. Okay, so that's why. The actual load is 17.5 kW, which is what's driving this value. If we needed to update this to 18, I guess the best way to do that would be to increase the leaving air temp. So in this case, we could use the leaving air temp override. You know, and I'm not sure why the team selection didn't have a 17.5 kW option, but either way, let's raise this up slightly. Well, that's a little too far. So 96, and there we go. Now we're at 18 kW. FLA, MCA, MOCP all match the given selections. Last thing is to verify zone heat loss. So let's look at our loads again. So zone heat loss 15,191. Let's plug that in. And we've got 177% capacity covered. So it looks like we are good to go. So the important takeaway from these families is get your connections, get the airflow to the equipment sooner, get your loads into the Revit models sooner. And you guys will see some workflows coming that are just going to make this process look like a joke in regards to getting calculated airflow to your diffusers. And then you're just left with making some duct connections to the unit. So that is the VAV box performance family. Hope you guys enjoy.